All right. In this video, I'm going to talk a little bit about graphs of potential energy. What we're going to talk about is graphs of gravitational potential energy, so minus g big M little m over r, as we learned in the previous video. So if we graph that as a function of location, what we're going to get is something that approaches 0 as it gets really big, and then sort of falls off like a minus 1 over r function, and gets, blows up at 0. It goes to infinity at 0. So this is the sort of characteristic shape of that potential energy graph. And it's always negative, which might bother you a little bit. But actually, what you're doing there is you're keeping track of the total energy when you have a system like this. And so what you're looking at is how the system's total energy, its kinetic, plus this potential part, how they relate. And what's very interesting about accounting for the energy in this way is whether the sign of the total energy is positive or negative, because we know the potential energy is always negative and the kinetic energy is always positive. And so depending on how large the kinetic energy is compared to the potential energy, the total energy of the system might be positive or negative. Turns out that's a really useful thing to think about, because it tells you about whether the motion of a system can exceed some certain distance. So for example, let's take an object that's orbiting a planet. It turns out that the total energy for this system is negative because as we look at this, if we account for some total energy here, the total energy is equal to the potential energy at whatever this location is, which is the farthest this object might travel away from the other one. And so accounting for the energy in this way is a very useful tool, because instead you might have a situation where an object slingshots past some other gravitational object like this, and it goes back out to infinity. In this case, the total energy would be greater than 0 because really, really far away from the system, the object is still moving. It still has some kinetic energy. And so the total energy curve never runs into the potential energy curve. So the object can continue to go as far as needed and continue to move with some velocity. So that's one way of sort of thinking about why these two pieces of the energy interact the way that they do, and how having or thinking about the total energy being positive or negative is a useful thing. One other thing to do is to actually think about, does this graph actually demonstrate to you where this kinetic energy term is on it? So if we were to graph, instead of the potential energy, just the energy of these different functions, so what we're going to do is, as a function of r, we'll graph the potential energy. The total energy, we might say, of some system is overall negative, so that it runs into the potential energy curve at this location. So this is the total energy, the dotted line. So if we were to measure the potential energy at any of these locations, we would get a measure that goes down like this. So that's the potential energy at this location. If we move farther along, we see that that potential energy is getting smaller in terms of its size, right? The arrow here is getting shorter. Right at this location, the potential energy is exactly equal to the total energy. So we know that the kinetic energy here must be 0. It must get bigger as it goes along here. But the sum of the potential energy and the kinetic energy has to be the total energy. So it turns out the kinetic energy is the arrow which points from the potential energy curve up to the total energy line. So that's the kinetic there. So the sum of these two gives you the total energy. It gives you this little gap right here, right? And if we track that, continue to track that, there's the kinetic energy here. And we add those two together, they give you that little gap there. And you see that the total energy stays a constant, as we would expect for a system where you're only considering the potential energy of the two interacting particles and the kinetic energy of the smaller particle that moves around. At this location, where the potential energy is all of the energy is potential energy, there is no arrow that I can draw for the kinetic energy. There is no kinetic energy at this location. This goes back to the idea of bounded motion. On the other hand, if I were to draw this curve again, here's the, oh, that's a terrible drawing. There's the potential energy. And if we have some total energy that's positive up here, it is still the case that we measure the potential energy down from the 0 line. But we also measure the kinetic energy up from the potential energy to the total energy line. So here the kinetic energy is larger than the potential energy, which is why we have a total energy that's positive. And we can still see the same kinds of trends as we're drawing this along the way. Right? The kinetic energy continues to get smaller, but as the potential energy vanishes, as it goes to 0, the kinetic energy becomes the total energy. So this is unbounded motion. There's still some kinetic energy very, very far away for the smaller particle. So this is a way of thinking about both kinetic and potential energy on the same graph. The last thing to consider when you're drawing these graphs is why it is that for some restricted cases, we consider the potential energy to be something like mgy, which is what we've been doing in the past. And so if we draw that graph again of potential energy versus distance, we get some shape that looks like that. Let's consider now that we're close to the radius of the Earth. Let's say the radius of the Earth is roughly here. And so we're considering being very close to that radius. So we're going to take a small window of distance, if you will, like that, right? So just, a small portion of the distance above the surface of the Earth. And we're going to blow that up into a big picture. And if you look at that picture blown up, you're going to get something that kind of looks like that. So it's kind of straight, right? It still has a little bit of curvature to it. But if you zoom in farther and farther, right? So we zoom in a little bit farther on this, we're going to eventually get to something that has a graph that is very linear. And this linear graph, so now this is u as a function of r, this approximation is zooming in very close to this big graph, zooming in very, very close, and understanding that at that scale, at that very close scale, that this graph is now a linear graph approximately. And so we can calculate the gravitational potential energy as mg times the change in position. Or actually, that's the change in gravitational potential energy, because we're looking at how that changes linearly. In the notes, I've done the full derivation to show you how you get from here to here mathematically. But the idea is just you're zooming in on this potential energy graph and only considering a very small portion of it. So that's it. That's graphing potential energy.